All right, well, our second lecture from Natasha.
All right, so thanks for coming back. I didn't scare off everybody yesterday. And today is going to be something slightly different. I was going to say completely different, but it's not completely different. It's building on, but in a different direction of yesterday. So our outline for today is strong trees. What are they? Halperin-Likely theorem, a proof, which everyone should be happy about because this proof was not easy to come by. Millikan's theorem, and then how Millikan's theorem is applied to get theorems for big Ramsey degrees of infinite structures, in particular ultra-homogeneous structures. And a very brief nod to the connections between Ramsey theory and topological dynamics. And then, if time, Ramsey theory on uncountable trees and some applications to uncountable structures and open problems. All right, so strong trees. I'm going to just put up the definition. So we've got a tree. Bars T is going to denote its domain, which we call the length of T. We're going to be working with trees which are finitely branching with nodes coming from omega. And our definition of a tree here is slightly different from what you're probably used to because we don't want all initial segments necessarily to be in there. But what we do want is for the set of levels of the tree or lengths of nodes of the tree, we want it to be closed at those levels, downwards closed. And this is the notion of tree that is suitable to the strong trees, which is why I'm setting it up that way. Then our height of the tree of T in the tree T is the order type of its predecessors in T. And T of n is the nth level of T. And then successor is going to be the members of T hat, which are the set of initial segments now. So just immediate successors. And then we say that S is a strong subtree of T if there's an infinite set, so that every nth level of S comes from some level of T. And every member in the nth level of S, given its immediate successors, there's going to be one extension in the next level of S. So this is a bunch of words and notation. And what's it look like? It looks like this. Okay, so the nodes, this is an example of a strong subtree. It has nodes of length 0, 1, 3, and 6, and so forth. So this is not a node in the tree. It's just a predecessor, it's an initial, it would be a part of an initial segment of 2 to the less than omega, but it's not in the tree S, okay? So these are like isomorphic to 2 to the less than omega in my example, where levels, lengths, relative lengths are preserved. Okay, all right, here's another example of a strong tree. So hopefully the pictures are worth 1,000 definitions. And now some notation. We're going to be coloring level sets of trees, level sets and their products. So this big O times notation just means the union of the products of the nth levels of your trees. And the Halperin-Likely theorem says that when you have finitely many finitely branching trees with no maximal nodes, and our colors, then when you color your level sets into our colors, there's going to be some strong trees with the same levels so that C is constant on this product of your sub-strong trees. Right. So this is Halperin-Likely. Yes?
Like the very last line of the definition
of the first one, yes. There. Exactly one. Right, so what this is doing is saying you're going to be so let's just take to the less than omega because it's a good example. And your strong tree is going to have some node here. Then you're going to have two immediate successors in the ambient tree. And then each of those must have a unique extension in S.
So do you mean U is in the successor in T?
Yes, yes, whoops. Thank you. Yes. Right. And then the same idea, yes, successor in T, and then going up through here to some level, and okay, yes. All right, so the Halperin likely theorem, yes.
Sorry, that very last formula, that's, you don't need the bracket there.
Where?
C's constant. But you have the brackets there?
What bracket?
At the very end, SI brackets N.
Yeah, oh, you're right. Thank you.
Right, it's really the product.
Yeah, right. So I'm going to write the theorem here, just for reference. Okay, so if we have Ti, some trees from omega to the less than omega, so what I'm meaning by having the same lengths, they have this one set of levels L. Every tree in each of these SIs have levels exactly in L, no more, no less. And then you're taking these level products. Yes, so a really interesting thing is that this Halperin likely theorem, how it came about was looking into how do the axiom of choice and the Boolean prime ideal theorem relate? Were they the same strength or was one weaker than the other? And then in the process of proving that Boolean prime ideal theorem is actually strictly weaker than axiom of choice, this combinatorial lemma was the heart of the proof. The original proof is in really like first order logic language, and somehow somewhere along the line people decoded this into trees. All right, so now we're going to give some examples of colorings of level products so you can see what this means in two trees. So here's a tree T0, here's a tree T1, here is their product of level 0. I'm coloring the product red. Now here is the product of level 1. So I'm coloring this red, these two blue, and these two red, right? So you're taking all the possible products, and this is what makes it a stronger complexity than just the Ramsey theorem. Okay, so you get the idea. These are the sorts of things we're coloring, etc. And we're looking for strong subtrees with the same levels where the products on each level are the same color. Okay. All right. So hopefully that gives you a flavor of what's going on for the Halperin likely theorem. And one of the first instances of an application of this was by Lever, who showed that if you take product of finitely many copies of the rationals as an ordered structure, then and you color into finitely many colors, then there's going to be some subcopies which are again rationals in the same linear ordering, so that their product takes at most d factorial colors. Okay, so this is a quick, an early application of Halperin likely to these large homogeneous structures. Okay, Harrington's forcing proof. Now, this is where a certain person in the audience wanted to be to hear this, so I'm going to go through it in quite a bit of detail because it's been hard to find a proof of this. And the way I got it was through Richard Lever just before he passed on. He gave me an outline and I refilled it. So this is my version via Lever of Harrington's proof of the Halperin likely theorem. All right, so let's start. We are going to fix D, at least 2. Well, it could be 1, but that's not really very interesting. So we're going to say it's 2, and let Ti be some strong subtrees, or just be some subtrees of omega to the less than omega. And we're going to fix our coloring, just say into 2 colors. And now our first key theorem we're going to put to work is this Air-Ratto theorem, which says that if you, so let me decode the notation in case you're not familiar. So for each coloring from Beth R of mu plus subsets of size r plus 1 into mu colors, there's going to exist an x, which is in Beth R mu plus to the mu plus, such that x is homogeneous for C. Okay. And what's the beauty of this theorem? It's that mu is an infinite cardinal, right? So you can take infinitely many colors and deal with them, whereas normally we're only using finitely many colors. So we're going to let kappa be Beth sub 2D so that we have this partition relation at our hands for aleph 1 size subset with aleph not coloring. And now we're going to make a forcing, which is a nicely neatified version of Cohen forcing to add kappa many Cohen reals. So P is going to be the set of functions of this form, where it's going to take D cross delta P into the trees, where delta P is going to be a finite subset of kappa. LP is the length of the range of the function. And for every D, the range of Pi delta is going to be contained in Ti of length LP. Okay, so sort of homogenizing the forcing where all of the nodes are going to have the same lengths and they're all going to have the same number of inputs.
What is kappa?
Kappa is this. right, and then the partial ordering is just extension, where we want the lengths to be greater or equal, and the set of ordinals that are indexing is at least containing the old ones, and then the ranges and extend.
So TI restricted LP, what's that?
TI, yeah. So TI restrict to LP for me is exactly the set of T's in TI such that the length is LP. So I'm not meaning the LPth level, I'm meaning exactly the length.
Yeah.
Yeah. So we're taking, if we have two trees, we're taking things, there's some LP level, and we're taking some nodes in here. We might take 3 and 4, but you have to have the same number of ordinal in each, so you might double up here. Okay, and this forcing is going to add kappa many branches through each tree Ti. And it's just a fancy form of Cohen forcing. There are several reasons I'm presenting this proof. One of the reasons is because it's the best way to extend to uncountable. It's the only way we know to extend to uncountable analogs. It was the means through which I proved big Ramsey degrees for the Henson graphs, and I didn't really see any other straightforward way to do it. And thirdly, it actually is the best proof, in my opinion, because it's the most straightforward, and it gives you an idea of what's going on, rather than the other proofs in the literature, which are you can parse through them, but they're a little bit harder to actually see why it works. So Harrington's forcing coloring, and we're going to put some names for our alphith generic branch through Ti, which is of course defined by that. And then if I alpha is in the domain, we note that P forces this alphith branch through Ti at length LP to actually equal Pi alpha. Then we're going to take a name for an ultrafilter, U dot on omega. So we're going to have an ultrafilter in our generic extension at our disposal. But really, we're just using the name. Now we're going to set up some notation. So alpha bar is going to be a D tuple written in increasing order. And then we're going to let B dot alpha bar equal this D tuple of the generic branches. And now we're going to start choosing some conditions so that we want to homogenize them in some large set of size aleph 1 eventually. That's where we're going. So we want to take some P alpha bar for each alpha bar in K to the D, so that alpha bar is in the set of ordinals in the domain. And we also want P alpha to decide a value for which it forces that value at this ultrafilter many lengths. And secondly, we want C at this condition to have that same value. Okay, so using general forcing technology, you can arrange this in several steps. And what it's going to do, okay, now we're going to set up the Ramsayology. And what I didn't cover yesterday, but what this is building on, is a proof by Ramsay of canonical relations on, say, n to the d, and that can be used to prove this Air-Ratto canonization theorem I alluded to yesterday. So if you go back and look at this Ramsey theorem number 1.7 in Todorczewicz's book, then you will see the same idea at work. Okay, so we're going to let I be the collection of functions from 2D into 2D so that its first two instances are less than the second two or less than that, right? But these could be equal. Iota 1 could be less than iota 0. Iota 0 could be less than iota 1, right? So we don't know how these two are related to each other, but we do know that the max of them is less than the min here, etc. Because those are the only sort of functions we need to worry about. And then given a theta of size 2D in kappa, iota of I is going to determine two sequences, namely the evens and the odds, by their indices. Okay. So note these two, of course, are going to come before in order these two, etc. And what this is setting up is our coloring. So as Labor said, you basically want to put all the information into the coloring that you need to know before we apply this Air-Ratto theorem. So our coloring, given your theta and an iota, make f of I theta to be this sequence of sequences, right? Where we're looking at what is the iota. There's only finitely many of those. What is your E alpha bar? There's two of those. What is your K alpha? This is the number of the size of your delta. Okay. And then what are the actual values of your condition? Right? List them out. We've got finitely many countable trees. Each of level has finitely many values. So this is a finite sequence, but it's unboundedly growing. Then we want to look at our pairs ij, which are giving us the jth entry of delta alpha being alpha I. So this delta alpha is some finite sequence of ordinals. We can enumerate them in increasing order. And which j gives you alpha I, that is this sequence. And then the last one is which j and k's give you the same value for the ordinal between alpha and beta. Okay. So this is going to give us a countable coloring. And for each theta, we're going to define f of theta to be the sequence of f iota thetas. Okay. So this is the coloring, this f of theta is our coloring that we're applying this Air-Ratto theorem to. Okay, so our domain is kappa to the 2D, range is a countable set. Apply our Air-Ratto theorem, take some k, which is homogeneous of size aleph 1. And then we're going to take ki's from k so that each one is countable. And all of these appear before k1, all of k1s appear before k2, etc. And we're going to make it thin in k so that we have a little wiggle room to do the Ramsay process later. So just think you've left out every other member of k in this unit. That's sufficient. And then we have a series of 4 lemmas. So lemma 1 is going to show that there's one epsilon, one kappa, one set of members of a level of the TIs, so that for all the alphas in this product, these are the same. Okay. And this is not hard to do. Let iota be the identity function. Then for any alpha and beta, there are some thetas where alpha is IE and beta is IE of theta and theta prime. And then you go back to your function f of iota theta and the fact that we were, that f is homogeneous is going to imply this. Okay, so we now have basically, we have some level. I'm going to call this L star. We have some nodes here, which are our Tij's. Coming from the P alpha bars. Okay. And what we're going towards is we're trying to prove that for all the alphas in Ki product, that these P alpha bars make a compatible set of conditions. Okay, so lemma 2 is going to show that given alpha bar and beta bar, if you have J and J prime, and the jth member of delta alpha is the same as the J primeth member of delta beta, then J had to equal J prime. Okay, so let's suppose this. Then we're going to let rho I be the relation which tells you what I alpha and beta alpha are doing, right? And then we're going to take iota in I, which matches these relations. And we're going to take theta in K prime to the 2D. So my K prime is the union of the Ki's. And such that the evens from iota gives you alpha and the odds from theta gives you beta. And you want to take a gamma using the fact that we left stuff out of the K prime. Now we're going to go back to K. We've got things between any two members of K prime. We're going to use those to fill in the gap. So we've got sort of like a transferring principle or a... So then we're going to take some mu bar and nu bar in K, where the evens from mu match alpha, the odds from mu match the evens from nu match gamma, and the odds match beta. And this is going to be our sliding principle. So delta alpha j equals delta beta j prime implies that this pair is in the last sequence of our definition of f, which means the homogeneity of f is going to tell you these are all equal. And then this is going to imply that these are equal, which is then if delta gamma bar of j is delta gamma bar of j prime, and delta gamma bar of the j's is listing them out in increasing order, that means j has to equal j prime. So if you wish, I can give you a little graphic for this. Okay. My work was not in vain. All right, so let's just go through an example. So this is lemma 2. All right, so we're going to have an example. Let's say D is 2. All right, so we've got some alpha naught. Let's suppose it's less than beta naught. And let's suppose that beta 1 is less than alpha 1. So these are coming from K naught, and these are coming from K1. And in this case where I've set it up, we're going to have rho naught being less than, rho 1 being greater than. Because alpha 1 is greater than beta 1. And we're going to, okay, so iota is going to be, iota 0 is 0, iota 1 is 1, iota 2 is 3, and iota 3 is 2. Okay. All right, so the rows are telling you which iota to take. And now we're going to take gamma, not in K, so that we have alpha naught less than gamma naught less than beta naught. And we're going to take gamma 1 in K, so that beta 1 less than gamma 1 less than alpha 1. So it's sort of sandwiched in between. It's going to be an interpolation. You can think it's like an indiscernible in a way. And then we're going to take mu and nu in K to the 2D, such that now we're going to have mu naught equaling alpha, mu 1 equaling gamma, nu naught equaling those two, and nu 1 equaling beta naught. Then we are taking mu 2, mu 3, nu 2, and nu 3. Okay. So 2D is 4. All right, and so this is our sliding technique, and we're going through this as a very basic Ramsey idea. And we're going to take some sort of interpolants so that we can slide between alpha and beta via these mu and nu and end up with this, you know, gamma j equaling the gamma j prime up there. Right. So by homogeneity of F, so mu bar is giving us that delta alpha bar of j is equal to delta gamma bar of j prime, because alpha is iota e of mu and gamma is iota o of mu. Okay, so this is going back to F and the homogeneity of F and what these are interpreted as. Right? Then nu is giving you delta gamma of j equaling delta beta of j prime, because this is iota e of nu and this is iota o of nu. And then lastly, our assumption was that delta alpha bar of j is going to equal delta beta of j bar. So you go through these and you find, okay, they're all equal, and you end up with this. There. Okay. Okay, so that was lemma 2. Lemma 3 is going to be a little bit more straightforward. So now this is the main lemma of this proof, and we're showing that the p alpha bars are all compatible when alpha bar is in this product of the ki's. So we'll assume not, then there has to be two members of this which are incompatible. And by the lemma 1, that tells us that there has to be some j where the delta alpha j equals p of delta beta j. So this incompatibility implies there must be some I where these deltas are equal, but their values are not. Right, so you had same input, different value, incompatible, basic co-enforcing idea. And then note that the p alpha, delta alpha j's are always equal to tij. And so this has to imply that j is not equal to j prime, but then the lemma 2 implies that these can't be equal. Okay. So by homogeneity of F, there's going to be a strictly increasing sequence of these ji's so that delta alpha ji gives you alpha I. So this is how we can recover our original sequences knowing the delta alpha bar. And for each alpha bar in this product, the p alpha bar I alpha I is equal to this ti ji t, which we're going to call ti star. All right, what's the point? So the point is these ti stars and lemma 3. Okay. So the ti stars are going to tell us where we should start making our homogeneous subtree. So what this all did was basically an unbounded search for a good starting point. Right? Because part of the problem is you're trying to make these homogeneous subtrees. Well, you don't know where to start. And if you start bad, you're sunk, right? So this forcing idea told you, where should I start? And now I'm going to be okay to keep extending in the same color because the set is homogeneous, is compatible. So what do? We've got T0, we've got T1, and we've got some magic points. And these are equal to P alpha bar I, sorry, that's 1 alpha 1 for each alpha bar in this product. And this is equal to P alpha bar 0 alpha 0 for each alpha bar in the product. All right, so we're going to build our trees now. So we're going to let the stem of Si equal to Ti star. We're going to now, at the mth part of the construction, assume we have m strong, meaning m levels of the strong subtrees, so that C takes the same color, epsilon bar. And now we're going to take your immediate extensions of Ti, of these nodes, and let Ji be some set of ordinals of exactly that size. We're going to label the nodes in there as these nodes in the tree using these ordinals. And let J bar be the product of these Ji's. Then for every alpha bar in this product, this Q alpha I is extending the Ti star. Okay. And then we have our lemma 4, which says that there's going to be a condition that's below each of these P alpha bars. And the proof idea is that you have let delta bar Q be the union of the delta bar alphas, where alpha bar is in this J bar. And then for each pair that wasn't taken care of by this process up here, you note that there's going to be some alpha bar and a J prime where this gives you that gamma. And by the lemma 3, all of these beta bars and J bar with this gamma in their delta have this same node in their image. So you're going to just take a Q of I gamma to be the leftmost extension of there. And this is how we're going to make sure we fill out. It's basically like you're taking the union of the P alpha bars, alpha bar and J bar, but then you've got to fill out to make sure that you have a condition. Okay.
So lemma 4 says more than what's written there.
Yes.
Yeah.
So
wanna, yeah, you wanna cover those two i's, right?
Yeah,
You
so.
wanna cover the x, the capital X i's.
Right, so I don't think it says more than what's written if you take this into account.
Well, you already deduced that the p alphas are pairwise compatible.
Yes.
So Lemma forces, you know, just something weaker. P alphas are pairwise compatible, so pi and p.
That's true. That is true. Yes. This became an issue in the triangle free, which I think I was overthinking.
I mean, you
to make sure it extended.
Extension which does something with
But
the nodes xi, right?
yeah, you want to make sure that you have a common extent. I think you're right, though. I think you could just take the union and then say it exists because they're compatible. I think I was overdoing it. Yeah. Yeah. So in this setup, what this is looking like is we're taking our immediate extensions. I'm going to take some alpha naught and some beta naught, some alpha 1, beta 1, and we're going to make this be p naught, alpha naught, p naught, beta naught, p1. I think the thing is, though, why I'm being careful is because I don't just want any old extensions, but I want it for this particular setup. I mean, so this is the x naught here, this level, and I want to take some. No, I think you're right. I want to take some ordinals alpha, beta in k naught and label these as p0 alpha naught, p0 beta naught. And these here, and then for all of these possible correlations, you're going to make the p, I'm going to say gamma bar out of these products here, which is going to have these as particular members of their ranges. And then you're going to want to take something that is extending each of those, which we know we can do because it's compatible. And yeah, it's fine. I'm just being like super detailed about it, but yeah, you could just take the union. Okay, so constructing the SIs, what we're going to do then is we're going to take an R, which is extending this Q. Sorry, those were Qs. And this is going to give us some level. We have R0 alpha naught, R0 beta naught, etc. And we're going to take the R so that using the ultrafilter name for all the alphas in J bar, we have the same color at this level. So we're basically doing finitely many searches here, finding this R where these are all equal. And then it's simply true, okay, so then the miracle occurs. And it's simply true in the ground model that the coloring of these nodes is epsilon star. Because this is actually the Ri alphas. So this level, and we take it, and this is our level S of 1. And then we do the same thing again. So then we would take these immediate extensions, make some condition, extend it with the forcing, use the fact that we had ultrafilter many of the same levels with the same color, take those and keep going.
Yes, you wanted to find a common extension of the P alphas for alpha and J bar, which also force that those generic branches go through your x0 and x1 sets, right? Yes, it's not any, that was my concern. It's not any common extension of the P alpha, because your lemma, the last lemma you had on the slides, it said just pick any extension.
Yeah.
Right, I mean, literally what was written there, that there is a common extension.
Yeah.
The union is a common extension.
Right.
But it does not necessarily force that the right branches go through your points. I mean, you fix those points, right?
Yeah, you want to fix the points.
You first fix the points, then you have the lemma.
Then you make.
If you go back.
Yeah. You want to first.
Right, you fix the. What was it? You fix the xi's.
Yeah.
Right? So you want that the generic branches go through there.
Definitely.
So that's what you make sure, that Q forces this and also extends the P alphas.
Yeah.
Right?
Yeah.
So lemma 4 says a bit more than what's written. I mean, that's why I wrote
I see what you're saying. Yeah, yeah.
Yeah.
Right.
Because the x side won't appear.
Right. Yes. So what I really meant there was that this Q is containing these. Yeah. Yes. Okay, and then have the same color epsilon star, so we're done. Right. So it's a great use of forcing in probably the old-fashioned recursion theory way, because we didn't actually go to a generic model, we just did a search.
It would be enough to find the monochromatic set in the extension, though, right? I mean, then you have conditions which, longer and longer conditions, which decide where the trees are, and then that tree is in the ground. It's an absolute concern that you have a this countable object in a CCC extension. You know, your requirements on the countable objects are decided on finite initial segments in monochromatic, so compose better.
Isn't the statement of the theorem like 512? Like for any coloring there exists coloring exists in the ground.
For each coloring in the ground model, there exists the trees. Yeah. All right, so the Halperin likely theorem is going to be the basis for this next theorem, which is Millikan's theorem. And it says that if you have some finitely branching trees with no terminal nodes, and you have a coloring of k-strong trees, subtrees, where k is fixed, into some finitely many colors, then you're going to find a strong subtree where all of the k-strong subtrees have the same color. So the proof goes by induction using the Halperin likely theorem that we just proved, and I'll give a couple of examples. So let's say k is 3 and we're coloring 3 strong subtrees. So here's an example. Here's another example. These are the objects we're coloring. Then Millikan's theorem is going to give you a strong subtree in which all the 3 strong subtrees have the same color. And just a nod to yesterday's lecture, Millikan proved a couple years after that first theorem that the space of strong trees is actually a topological Ramsey space. So this theorem is, as stated, is like saying that ARK has the Ramsey property in this Ramsey space. All right, and the L-tech topology on the basic is given by your basic open sets, where you have a finite initial tree and then all of the strong subtrees which are end extending that finite initial tree. All right, so let's recall again Infinite Ramsey Theorem. So this is my segue. So given n and r, you have a coloring of the n tuples of n into r colors. You're going to find an infinite subset, which is monochromatic. So note that n is isomorphic to the original structure as linear order. And this leads to the question of which infinite structures actually possess these infinite analogs of Ramsey's theorem, where you want to preserve the original structure. All right. So one application of Millikan's theorem is to the rationals. And first of all, if you have a finite coloring of singletons of the rationals, of course, we know we can find monochromatic subset. But if you're going to color pair sets, then there's this coloring of Sierpinski, which is going to make sure that every copy of the rationals takes both colors. And the coloring just goes by take a well order of the rationals, and then color your pair red if the linear order and the rational order match, and green if they don't match, and then every copy of the rationals has to have both colors. And furthermore, given any finite number n, there's going to be a number t of n, so that any coloring of the n-size subsets of the rationals can be reduced to exactly this number of colors. And this was a theorem due to Lever, and then the exact numbers are computed and found with a lot more work by Devlin in his PhD thesis. And these numbers turn out to be actually the coefficients of the Taylor expansion of the tangent function, which is sort of a strange anomaly. So this is the beginning of big Ramsey degrees.
This is the Ramsey theory, Devlin, not the diamond Stanford Devlin. Right?
Sorry?
Sorry?
Yes. It's Dean Devlin.
It's Dean.
Yeah, Dennis. Yeah. Not Keith. Yes, so the idea, okay, we're going to use strong tree envelopes. So you can, of course, code the rationals into the less than omega via this ordering. And given n, the number of types of finite trees, which is coding an n tuple of rationals, is finite, right? If you have a pair, it's going to either look like, like that, or like that, because you can thin your rationals so that only one appears at each level in your tree. And basically, you're going to take some strong subtrees, which subsume them, and apply Millikan's theorem once for each of the types. And then do a lot of work to make sure that you took the thinnest and best copy of the rationals inside the tree so that you get these exact numbers. Okay, so this is where combinatoric set theory, model theory, and topology meet. It's a nice area. And so what are big Ramsey degrees for infinite structures? Given structures A and B, where A embeds into B with this notation, we're going to let B choose A, denote the set of all copies of A and B. So given an infinite structure S, we say that a finite substructure has this number of degrees if, given any coloring of your copies of A and S, there is going to be an S prime isomorphic to the original structure, where C takes no more colors than this number T. Okay, so this was thought about for many, many years, but the phrase finite big Ramsey degrees was coined in this Kekres-Pestov-Todorcevich paper in 2005. Okay, so then this begs the question of which infinite structures actually have finite big Ramsey degrees, and this is an area of quite a bit of interest in homogeneous structures currently. And the first sort of recent result on this was on the Air-Ratto graph, which was due to Norbert Sauer. And vertices, so the Air-Ratto graph is the random graph. It's the same thing as, you know, flipping a coin if you have an edge or non-edge. But I like it best as universal ultra homogeneous, because universal means that every other countable graph embeds into it. And ultra homogeneous means that you have this extension property where if you have two finite graphs that are isomorphic with an isomorphism between them, you can extend it to an automorphism of the whole Air-Ratto graph. So edges have big Ramsey degree 2 due to Pouzet and Sauer. And then all finite graphs have finite big Ramsey degrees using Millikan's theorem. And then the actual degrees were found structurally in this paper and then computed by Jean Larson in terms of sizes of graphs, not particular graphs.
I'm sorry, could you go back?
Yeah. Oh, yeah. Yeah. All right, so I'll rewrite this over here. All right.
So,
Yes.
it's like, so vertices have big Ramsey degree 1 means if you color the vertices?
Means if you color the vertices in finitely many colors, there's a copy of the Air-Ratto graph with one color. Yeah, so if you partition it into finitely many, it's also called indivisible. So if you partition it into finitely many pieces, one of the pieces contains a copy of the Air-Ratto graph.
And edges just means you color pairs.
Means you color edges.
Yeah.
That's not
Okay.
Yeah.
Yes, I see, because you only care about the graph relation.
I mean, you could color all pairs, but some of them are irrelevant. Yeah. Then you can also color non-edges. Right.
in the third line, you actually mean that the Air-Ratto graph itself has finite big Ramsey degree.
Edges have big Ramsey degree too in the Air-Ratto graph.
Third point.
The third point.
All finite graphs have finite big Ramsey degree in the Air-Ratto graph.
So does this mean that the Air-Ratto graph itself has finite degree?
Yes, 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 yes.
The TAs are
Yeah.
finite.
Yeah,
TAs
exactly.
are finite for all finite.
Yes.
Okay.
Yes. Yeah, that was a big deal
Yeah.
to show that for all of them simultaneously. Yeah. So I'm going to go through some pictures now. So these are colorings of graphs. Here's an ordered graph A. Here is an ordered graph B. Here are colorings of copies of A and B. In this case, the order matters. There's a theorem of Neshatril and Riddle that shows, and also Abramson and Harrington, that show that this class of ordered graphs has the Ramsey property. So whenever you have a finite graph that's ordered embedding into another ordered finite graph and you color, there's going to be a larger but still finite one where you have the Ramsey property between them. Okay, that's what I just said. And Freisey classes of finite graphs have finite small Ramsey degrees, which I'm not really going to go into, but basically that just means this, but for finite structures, you have these finite bounds rather than one color. All right, so now we are going to nodes coding graphs, nodes and trees coding graphs, which is why we went through the Halperin likely and the Millikan theorem before. So here's A. A is a graph. In this case, it's just a path. You can enumerate the vertices of your graph. And a set of nodes in a tree is going to code your graph A if and only if for each m and n, you have an edge whenever t on input length of m equals 1. Right? So here is T1 supposedly coding V1. Let's see, as T1 passes by T0, it goes right, which means that T1 of input length T0 is 1, which means it codes this edge. And then T2, as it passes by T1, has input 1, so it codes this edge. And T2, as it passes by T0, is 0, so it has no edge from V0 to V2. Okay, so basically the idea for this came from Erdős, Heinel, and Posa, where if you take the edge relation, you can make a lexicographical ordering on that. If you interpret the lexicographical ordering into a tree, this is what you get. All right. And not so super important for today, but just an FYI, you have certain trees which are diagonal and strongly diagonal, and the point is that you're making subtrees which have some nice thin structure so that you don't have too many types. It's trying to reduce this number TAS, is what these diagonal trees are doing. And every graph can be coded by, terminal nodes of a diagonal tree. And so let's look at a couple examples. Here is a different strongly diagonal tree coding the same path. Right? It has a different tree structure. And here are some strong tree envelopes of this tree coding the path. So these red nodes are coding that path. And here is a strong tree envelope helping you go from the tree coding your graph into the Millikan theorem. Here's a different strong tree envelope. But the point is that for every finite graph being coded, you're going to have only finitely many strong tree envelopes. So the envelope takes into consideration where's the meets and the terminal nodes of your graph. Okay, so Sauer's proof, how does it go? The Ratto graph is bi-embeddable with the graph coded by the nodes in the tree 2 to the less than omega. So if you take the tree with 2 to the less than omega, you take that coding of edges, right versus non-edge being left, and you make that into a graph where nodes at the same level don't code edges between each other. That graph always embeds the Ratto graph. And of course, by universality, the Ratto graph always embeds that graph. So you can sort of work between the two. Then he points out that each finite graph can be coded by finitely many strong similarity types of these strongly diagonal trees. Strong similarity type is taking into account the tree structure, where you go right, where you go left, where you split, and that's it. Then each strongly diagonal tree can be enveloped into a finite strong tree. And you apply Millikan's theorem finitely many times, once for each of these types that's coding the finite graph A that you care about. And then he chooses a strongly diagonal anti-chain which codes the Ratto graph. So the terminal nodes are coding the Ratto graph. And then they show that every subgraph of this in this strongly diagonal anti-chain is going to preserve these strong embedding types. And that gives you the exact number of the TAs in the Ratto graph. So this is the upper bound for this big Ramsey degrees in the Ratto graph, and then the lower bound is with some more work. Okay, so other big Ramsey structures, ultrametric Uri-San space, Qn, which is the rationals with n many equivalence relations, and that's just an FYI. And all of these either have, well, this one has the Ramsey theorem at its core, and this one they make an extended Millikan's theorem to apply to get this. All right, so and then some recent work, which I'll talk about tomorrow, is the Henson graph HK, which is the analog of the Ratto graph for k-click-free. And these also have finite big Ramsey degrees by building on what I've presented today. All right, and then some other stuff that several of us are currently doing. All right, so a quick nod to connections with topological dynamics. The KPT paper proves a correspondence between Freisey classes and extreme amenability of their automorphism groups. More recently, Andy Zucker proved a correspondence for Freisey structures, which are the Freisey limits of Freisey classes, so these ultra-homogeneous infinite structures, between having finite big Ramsey degrees and universal completion flows. So this is our connection into dynamics. So, of course, the more of these structures we know, the more examples of these we have. All right, so we do have time to do the uncountable height trees. And the first move towards this was on measurable cardinals. Why? Why would you jump so high? Why wouldn't you just do L1 or first inaccessible? Because this is what works. So that's how research progresses. So Harrington's proof, his forcing proof, paved the way for the uncountable investigations. And Shela was the first one to put it to work, where he showed that it's consistent with ZFC plus the existence of a measurable cardinal, that on one tree of height kappa, so taking 2 to the less than kappa, and then taking m size subsets of the levels, into less than kappa colors, there's going to be a strong subtree in which the coloring is homogeneous, monochromatic. And his proof, I'm not giving a proof here, but his proof is basically a glorified Halperin-Likely Harrington argument, where the point of the measurability is that if you start with a strong enough cardinal in the ground model, that U dot name for, you take a name for an ultrafilter which is normal in the extension on kappa, and in order to make sure that that behaves nicely, because we took finite intersections in the argument before, well, now we need to take less than kappa intersections to make sure that you get one coloring, because your level sets are getting wider and wider. You need the measurability for that.
Do you say coloring takes only fine feeling color?
Actually, yeah, no, I think that's a miss. It can be up to less than kappa. Actually, what? Oh, here. That is a typo. That is a typo. It's one color. That's a very bad typo. It's a horrible typo. Yes, one color. One color. And then about a decade and a half later, Jamonia, Larson, and Mitchell sort of souped up this statement and then applied it to the kappa rationals and the kappa rattograph to get the analogs of the Laver-Devlin result and the Sauer result. But this left open questions about more than one tree. So when Dan Hathaway was a postdoc with me, we worked on this. And so T's we're going to call a regular tree if it's a kappa tree and all the maximal branches have height kappa. And same notation as before. Then HL delta sigma kappa says that if you have a sequence of regular trees and a coloring into sigma many colors, you're going to have a sequence of strong subtrees with the same set of levels, where C is monochromatic on their level set colors. So, and then there's a somewhere dense version, which we're going to do on comparison. So cones are cones. And we're going to say that X dominates Y if for every Y there's an X which extends it. And then the somewhere dense Halperin-Likely theorem states that given some regular trees and a coloring, there's going to exist some levels so that given your TIs at level zeta and some XIs extending these zeta primes, you're going to get XIs which are dominating on the cones of zeta plus 1. So you've got, something like, some nodes here. We're going to take their immediate successors, and then we're going to dominate at these XIs. That's the zeta and the zeta prime there. So you're only looking for one set which is extending. And in the countable case, these two are, is not horrible to prove that they're equivalent. In the uncountable case, we wanted to find out if they were still equivalent. And some big questions which are open in this area is whether the HL can hold in ZFC for which kappas? Or do you always need some large cardinal assumption to get them? And the second is, what is the consistency strength anywhere, and in particular for measurable? And what about the various versions of the Halperin likely theorem? If you look in Todorovich's book, there are about 5 different related but not necessarily the same statements for Halperin likely and ZFC for countable. They're all equivalent, but when you move up to uncountable, they may or may not be. So one of the things we proved was that these actually are equivalent, and that for every infinite cardinal kappa, SDHL with one tree simply holds. Okay, and then this was improved later by Jing for less than kappa colors and a stronger asymmetric version. Then we proved that if you have D, some finite number, and kappa being a kappa plus D strong cardinal, status in some model satisfying GCH, then there's going to be a forcing extension in which the kappa remains measurable, and you have HLD sigma kappa. Okay, so definitely, I'm sure everybody here knows what a strong cardinal is. Well, maybe almost everybody. So is kappa plus G strong if there's an elementary embedding with critical point kappa and it preserves kappa plus D much of the big model? So this theorem, right, if you went through the Halperin likely proof that I gave before and you just bumped everything up, you would get the result. The result being true is not anything exciting, like anybody who's worked with this would know that. But you would be doing it from a kappa plus 2D strong cardinal is the difference, and we were able to move it down. So my conjecture is that this is actually the consistency strength for various reasons, because, well, I'll mention it later. The theorem I mentioned on the previous slide goes through this as one of the pieces of its proof, and assuming some partition relations and kappa measurable after you've forced to add lambda many Cohen subsets of kappa, then this holds. So it's possible that there might be some good models of determinacy where these hold for delta being infinite. We don't know. And so if you get a copy of Todorovich's book, that's not really readily available, the English version of the Russian version, which is in print, then you will get a proof of the Halperin likely theorem, which uses forcing, but it's different than the argument I gave. And the difference is that they have a weaker assumption on the partition relation cardinal, so you don't have to assume as much, but then you have to do more work to get it. And their arguments gave us an idea of how to do this, bring down the upper bound, but we had to do some tweaks because the straightforward tweaking doesn't work. So the measurable cardinal actually was important to have to make it go through. Okay, tail cone version basically says that you're going to have many, many colors, and then at each point in your homogenized tree in a cone, you're going to have one color for each. So for each coloring C zeta, you're going to have some level after which on the cones C zeta is homogeneous. And this was proved by Jing, assuming kappa plus 2D strong cardinal. And the interesting thing is, so in order to get the analog of Leber's theorem for products of D many kappa rationals, you need this tail cone version to do it. and you can't get it from just the regular version. So it may be that you really do need this kappa plus 2D strong to get the big Ramsey degrees for kappa rationals products, which is why I make my conjecture before. Okay, effects of forcing are going to, so basically, if you have HL with your size of your forcing, then HL is going to hold after you've done the forcing. So the handy version is that small forcings are going to preserve Halperin likely once you have it. And likewise, the tail cone is preserved by small forcings. And if you have kappa being strongly inaccessible or cofinality uncountable, and kappa being a limit of strongly inaccessibles, then you're going to have HL for stationary mini alpha below kappa, implying HL at kappa. So you get a reflection upwards. And then you get also a reflection for measurables. And if you force with basically a kappa closed forcing, then you're going to preserve HL also. So at non-weakly compact cardinals, we have a few results. It's going to hold at every strongly inaccessible for one tree. And for more than one tree, it's consistent to hold at non-weakly compacts. But you have to have a large cardinal to start with to get there. So these are some open questions from this talk. One is to prove some lower bounds for big Ramsey degrees cohere so that you can have Zucker's work applied. This is true for the Air-Ratto graph. It's been done, but for other structures, it's not been done yet. Big Ramsey degrees for other ultra-homogeneous structures. Are there other means for proving big Ramsey degrees besides going through Millikan's theorem or some analog of Millikan's theorem? And then for Halperin likely, we're interested in consistency strengths for measurables, whether this tail conversion really is stronger than this in consistency strengths. Are there any forcings which destroy Halperin likely? I mean, the big open question for uncountable Halperin likely is it just true anywhere, or is it not true anywhere? And in particular for strongly inaccessibles, yeah.
What if you just ask about omega 1?
So omega 1 doesn't make sense for the strong tree version because you're going to get too wide too fast before you get there, because we're assuming that you have all maximal branches have maximal length. So this is the smallest one we would look at would be strongly inaccessible.
Singulars? Can you imagine like singular compactness for the...
I have not thought about that. It's either trivial or hard. We could probably find out in 3 minutes. And then references. Yeah, so if you go through my slides from yesterday's talk, at the end there will be a whole bunch of references there in case you're interested in looking up these things further. So, thank you.
Thank you. Any questions? Okay, then let's take Natasha.
Great.